Okay, it's time, so we're gonna start. We have stopped at lecture 3 last time. Okay. The lecture has started, so could you please remain seated and silent? The plane is going to take off. We have started. So, lecture 3, linear data structures. We have started last lecture talking about what we mean by the term data structure, and we said that different algorithms might behave differently or might have different efficiency if we pick different data structures. So our first data structure that we have seen was the array, and in terms of our talk about efficiency, what we said is that the array is a contiguous data structure, which means all the elements inside the array are adjacent to each other inside memory. So if we have a cache memory in the system, this is going to be beneficial for us. This contiguity also gave us this property that access time in the array is constant. We said access time in the array is constant. It's because the cells are next to each other, and we are able to compute the index of each cell in the array using a very simple mathematical operation. Okay, so in order to access an array, we said it's going to take us big O of 1 because the elements are next to each other, adjacent to each other, and we use a simple addition operation to compute the index of any element. And because arrays are in memory, and memory has a random access, so anywhere in the array, be it at the beginning, in the middle, at the end of the array, access is always the same. It costs constant time. So this is the access time of an array. We talked about records, and we said they are similar to arrays in the sense they are also contiguous in memory, and accessing any field of the record is always going to be big O of 1, just like the array, for very similar reasons. Adjacent cells next to each other in the record, we call them fields. And in order to compute the address of the field in main memory, it's again a very simple mathematical operation, which is addition in this case. In terms of programming, they are different because arrays, they hold elements of the same type. A record have fields not necessarily of the same type. We said that in order to insert something in the array, we might need to shift elements. If we are not inserting at the end of the array, we need to do some shifting of the elements, and in the worst case, we can shift as many elements as there are full or filled cells in the array. So for an array which has size n, in the worst case, if we are inserting something, we need big O of n shift operations, and that's why the cost of insertion in an array, inserting something, we need big O of n shift operations, and that's why the cost of insertion in an array is big O of n in the worst case. And also, when we said when we delete something from the array, we don't leave the place empty, because the semantics of the delete operation dictates that in order for something to be considered deleted, the actual cell must be filled in with something else. So we need to shift elements, and that's why, again, in the worst case, deleting, for example, the first element of an array which is completely full is going to require us n-1 shift operations. So again, deleting from an array requires us big O of n, where n is the size of the array. So these are the things this is what we talked about last time. And then we started talking about linked lists. And I believe you have done something about linked lists in the practical. So you are all happy with what a linked list is. Do you have questions about linked lists? So when you look at the slide in front of you, it makes sense to you. Okay, so just very briefly again, a linked list is used when we don't know in beforehand, when we don't know the number of elements that we are going to deal with. So we use a data structure which is dynamic, in this case the linked list. The linked list grows as we add more elements to it. The list has got a head pointer at the beginning which specifies where the list starts, and each time we have a new element we stick it to the element that we have added at the last time. By stick it, we are talking about this arrow which is the pointer, and this pointer in terms of what's happening inside main memory is just an address. So we create a record for the element, we add a new field to the record. This new field is just a pointer. It points to some place in memory where the new record is. So if you understand the slides, you said you understand it, so you already know what is a linked list and how it's represented in main memory. Okay, so like we have seen with arrays, so in terms of arrays, we talked about access time. How much does it cost to access element in location I? And we talked about deletion, and we talked about insertion. So we are going to do something similar with linked lists. We are going to estimate how much these operations cost. Okay, so if I use again my okay, so we have, let's say we have the following linked list. It has the elements A, B, C, D, and D does not point to anything. So this is a linked list of 4 elements, and we have also an array of 4 elements. It has B, A, B, C, and D at indices 1, 2, 3, and 4. So that's one is the top one is a linked list, and the bottom one is an array. And if we want to access A of 3, we are going to find it's equal to C, and we do that in big O of 1 because we are able to jump directly to this location in main memory. Now, when we want to access the third element of the linked list, it's not straightforward because we don't know where the element is in main memory. We cannot compute the address. The address of this element, we know it in main memory. It's very easy. We just add the index to the start address of the array. So we add that to the start address, and we know the address in main memory where the element C is stored. But in the linked list, where is the address of C? Where is it stored? Inside the linked list, how do we get the address of the element C? Huh? The pointer of the previous one, right? Okay, again, in main memory, this looks something like so. Let's say this is C, this is A, this is B, and this is D. And we said, so let's say C is at address 100, A is 200, B 300, D 400. So A points to B, so A is going to store 300, which is the address of B. B points to C, so B is going to store here 100, and C points to D, so C is going to store 400. D doesn't point to anything, so let's say there is something like -1 here to signal the null pointer. So in order to find the address, so we want to access C, and C is at location 100. So how do we know 100? Where do we get it from? From B, yeah, exactly. So we need to be at B. So, and B is 300. But how do we know B is 300? From A, exactly. And A is at 200. 200 we know. We know the start, which is this is the address of the pointer. The pointer which is at the beginning of the list. If we look here, this is where 200 is. This is the first pointer, and we know the address of the first pointer. It's 200. Okay, so 200 pointing to A, and this pointer is telling us that B is at something like, what was it again? 300. So this is 300, and B is pointing to C, and C is address 100. So in order to get to C, in order to find what is C, we need to go to B. In order to find what is B, we need to go to A, etc. So in order to access the element C, we have to go through from the beginning of the list and traverse all the elements until we reach the element that we want. Now, when we have the case of the array, that's not the case. It's not similar, because in order to access the element, in order to access the element C, all we have to do is to add the index of C to the start address of the array, and we are there. But in the linked list, we cannot just add. We cannot add the address we cannot add the position of C, which is 3 in this case. We cannot add the position to the start address of the pointer. Okay, we cannot do that. Now, can you tell me why we cannot do that?
Because the array it's order, and the structure of any array based on shift right or shift left. You want to add anything.
Okay, what you mean is that the array is contiguous in main memory, right?
Yeah.
So this is at 100, this is 101, 102, 103. This is why we can add the position to the start address. But in the case of linked list, it's not. If we add 3 to the start address here, we are not going to get the address of C, because C is not necessarily behind B or underneath B, and B is not underneath A. They can be in different locations in main memory. So this is why we cannot add addresses, an index to the start address. So in order to find C, we have to go through A, B, and C. So I hope now it's clear why the access time here is not constant. So what is it? So what is the complexity of accessing an element in a linked list? Huh? In the worst case. And what is n? Number of elements in the linked list, or the size of the linked list. Yeah. So if the size of the linked list is 100, in the worst case, in order to access an element, we take 100 steps. In this case, the worst case is accessing the last element of of the linked list. So we said we are always interested in the worst case. So the worst case access time is when we are trying to access the last element in the linked list. So it's big O. So the complexity of accessing an element in a linked list is big O of n, where n is the size of the linked list, i.e. the number of elements in the linked list. Now, I want to, so we have elements 1, 2, 4. This is the linked list, and I want to insert 3, 4. This is the linked list, and I want to insert 3 between 2 and 4. So this is insertion. Again, let's compare to the array. So that's an array, 1, 2, 4. That's an empty space. And I want to insert element 3 here. So I want to insert element 3 right here. And I want to insert that. So we said this one is going to be big O of n, where the size of the array is n, because we need to do shifting. Now I want to insert number 3 inside this linked list. How do I do that? Okay, you want to shift. So 1, 2, 4, and I want to add 3. 1, 2, 4. 1 is at address 1000. 2 is at address 200. 4 is at address 4000. So 1 points to 2, 2000. 2 points to 4. Right, and I want to insert 3 and between 2 and 4, and you're saying I should shift. Huh? Okay, just 1 please. Okay, great. So we put 3 somewhere. Let's say we put 3 here at address 5000. And then we change what? 4000 to 5000. So now 2 is pointing to 3. And 3 points to, which is 4. Okay? The order in which we did it is wrong, because what we did, we said we changed 4000 to 5000, which means we basically we take that and put it here, right? But now 4 is lost, because now we cannot reach 4 anymore. So what we should really do is to leave this pointer here and first link this with 4. So when we put 3, we make it point to 4000. So now 4 cannot basically, we will have always reference to 4. So we put this first, and then we break this pointer by making it 5000 in this case. And now this is how we make an insertion and linked list without losing our nodes inside the list. So this is how you do the thing. This is how you this is how you do insertion inside a linked list. Now the in this operation, all we needed to do, we needed to spell linked list. Now the in this operation, all we needed to do, we needed to allocate memory for this element. So we allocate memory, we make it 4000. So we already know the address of because we said we want to insert inside this linked list in this position. So we are here already, we are at this position. We know the address of 2 and we know the address of 4. So all we have to do is to put the address of 4 here and put the address of 3 here. So we did allocate memory, add an address here and add an address here. So if there was 1,000 elements here and another 1,000 elements before, all we have to do again is allocate memory for the new element, change this address, and change this address. And we know that in order to access, because we know the address of the element in main memory, so we can go to it straight away because it's random access memory, RAM, right? So we get to this point in big O of 1 because we can jump to it. We know the address already because we know where we are going to store where we are going to insert the element. We know here. We know the address of 2. We know the address of 4. So we just go to address of 2 and in big O of 1 time and make the assignment in big O of 1 time. Go to this address here in big O of 1 time. Make the assignment in big O of 1 time. So all we have to do, jump, read the address from here, read the address from here, jump to the place in main memory and store the address, jump to that place and store the address. And this is going to happen if this has 1,000,000 elements, if it has 5 elements, if it has 1,000,000,000 elements, it's always going to be this procedure. In other words, it doesn't depend on how big the linked list is. So if the operation of insertion is not going to depend on how big the linked list is, then the complexity of this operation is constant. Yeah. It's big O of 1 because it does not depend on the input size. Okay? Now, deletion is very similar. All we have to do is break the pointer. Right? So we have 1, 2, 3, and we want to delete number 2. So what we have to do in this case is create a pointer from 1 to 3 and then break this and this. This will be in main memory, but since we are not referencing it, it will be lost. Okay? So next time, as long as the computer, as the CPU is concerned, 2 is some empty space. It's just garbage. It's just garbage value here. Okay? Once we disconnect it, this means it's garbage. And that's why in object-oriented programming languages like Java, there is something called garbage collector. This process is going to look for all objects like this which are not referenced, which are not pointed to. And it's going to do something about them, free the memory from them. Okay? But that's something else. So in order to delete, we just insert a new pointer and break these 2 pointers here. And this is going to happen if we have 3 elements or if we have 1,000 or whatever. It's the same operation which does not depend on input, and hence again the complexity is going to be big O of 1. Okay, so do I say something about that? So, linked lists, insertion, deletion is constant, access time is linear, traversal, just like the array, is also linear. In order to go in order to visit all the elements, obviously, we are going to do it linearly. Okay, 1, 2, 3, 4, etc. So it's linear. What I'm saying in the previous slide is, one problem of using linked lists is that we are using extra space because we have an element like 5, but we need to add an extra pointer to it, which is this address, which points to the address of the next element. So we add a new field to the record in order to store the pointer. So we are wasting space. This is what we said when we talked about the array, advantages of array. We said that we only use the data. We don't waste space on links. Okay, on pointers. Links is pointers. Okay, so when you use array, we don't use pointers, so we are saving space. When we use linked list, we use pointers, so we waste space. Now this is important for us, because we said in one of the lectures that we are talking about algorithm efficiency, and efficiency first means execution time, and then it means space. So if we have two algorithms that have the same asymptotic complexity, but one of them uses less space than the other, then the one that uses less space is the more efficient. When we do sorting, after your holiday, when we do sorting, we will see that there are some algorithms which have the same asymptotic complexity to do the sorting, but some of them have less space requirements. Some of them take linear space, some of them take big O(1) space. And the algorithms that take big O(1) space are better, obviously, because they are equal in execution time, but they're not equal in space usage. So this is the story about arrays and linked lists, and generally about their performance. Okay, so now we know how we look at an array from an efficiency window, and how to look at a linked list from the same efficiency window. The linked lists that we have seen so far, we call them singly linked lists. Basically, there is one node pointing to another node. Okay, there are also doubly linked lists. These doubly linked lists are basically, we have a node which points to another node, and this node also points to the previous one, and this one points to that, and this one also points to this. And this data structure is useful when we need to go forth and back, because in a linked list, if we are here, okay, this is A, this is B, this is C. If we are in B, we can only go to C, we cannot go back to A. In a doubly linked list, obviously, if we are in B, we can go to C, but we cannot go to A. And we also can go to A, sorry. See? So B here is only one direction, B here is two directions. So in some applications, it is useful for us to be able to... So B here is only one direction, B here is two directions. So in some applications, it is useful for us to be able to go forth and back. And this is why we use a doubly linked list. Obviously, we need 2 pointers per node, so we need more space. There are also circular linked lists. Okay, circular linked lists are basically, we have one node pointing to another, pointing to another, pointing to another, and then this one pointing to the first one. Okay, they are circular. So again, in some applications, we need to be able to start from one node and reach that node at the end. Okay, so in that case, there is no start and end of the list, because we said in linked lists we have a start pointer and an end pointer. In this case, we don't have a start and an end pointer. Everything can be considered as a head or a tail. However, when we program it, we obviously need to denote what is our conceptual or hypothetical start. Otherwise, we cannot program it. So these are variations of linked lists, and like we said, they all need pointers. They have the same complexity for adding elements or deleting elements or accessing elements. In this course, we are mostly concerned with singly linked lists. So this is for you if you want to do some further programming with these things. I believe you have seen that in the practical. Okay, so there is no point in going over that. So this is just an implementation of linked lists. Right. Now we are going to move to some what we call abstract data structures. We will see later on what I mean by abstract data structures. So far we have seen arrays and linked lists. Now we are going to see stacks and queues. So first let's talk about stacks. So a stack is basically a collection of elements. Each one we put each one on top of the other. So this is a stack of plates, and this is a stack of books. Now, what is important when we use a stack is to notice that the element that we put the last is the one that we take the first, right? So I have my geography book, and that's my CS book, and that's my geography book. If I only take the top element, then if I put CS last, it's the one that I'm going to take first. So let me ask you a question. Let's say you basically have 10 pieces of clothes, okay? And you put one, and let's say you are using a stack so that whenever you wash a new piece of cloth, you put it at the top. Okay? Now, is using a stack a good way of doing it? Now, can you use a stack in this way? Can you use a stack so that whenever you wash a piece of cloth, you put it on the top? Now, what is the problem with that?